Welcome back to Calculus. This video is going to be a bit more technical than most of them, I would say. So in the earlier video, I introduced local max and min with kind of the intuitive definition. The function's smaller here than it is everywhere else nearby. But there are a lot of fine details that usually we don't have to pay attention to, but it's nice to have kind of understand them a little better just in case some weird situation comes up. Sometime you're wondering, wait, is this even covered in what John said? And well, so that's what this video is for. So the first thing, I guess, is that local extrema, when we say the word extrema, that is just the plural for the Latin word extremum, and extremum means either a max or min. So a local extremum is a local maximum or a local minimum. So anyway, that's the first thing. An extreme point is a max or min. Okay, so let's remember our definition. So I tried to make this a little more precise for this video. It's not usually when you think of the definition of local max and min, you want to kind of just have this intuitive idea of how it works. But the formal definition kind of needs some more bells and whistles. So we have a local minimum if f of c is less than or equal to f of x for all the x nearby, right? But we do have to say we only need to consider the points in the domain of f. Okay, so fine. Of course you only want to consider points in the domain of f, right? Because if we're doing f of c and f of x isn't even defined if x isn't in the domain. So that's kind of obvious, but I wanted to make it explicit here. And remember, when we say x near x equals c, that means that we only have to be in some little tiny open interval. And that interval could be very small. If you have some peaks very close to each other, like a highly oscillatory sine wave or something, each one of those peaks count as a local max because the interval around each one only has to be really tiny. So the other thing I wanted to point out is that this inequality here includes the equals to. So both of these include the case where f of c equals f of x. And that might seem weird at first. You might say, well, shouldn't f of c be just less than f of x or just greater than f of x to have a min or a max? And, you could define it that way. I mean, you can define your words to mean whatever you want when you do your own math. But it turns out that when we do global optimization, if you have a constant function, you kind of want to say every point is where a maximum occurs. And for that, it's nice to have the equals be part of the definition. And we want to relate local mins and maxes to global mins and maxes. So we want local mins and maxes to work kind of the same way. So it is actually good for things we'll do later if we include the equals here, even if it seems weird at first. Okay, so just go with me on this. And this is pretty standard. I don't know that everybody does it this way, but it is pretty standard. So I just wanted to go over this kind of weird example. So I drew this function. Between points D and F, we want to assume the function's a horizontal line, even though it looks a little bit wiggly. That's just my unsteady hand drawing on the screen. But anyway, I want to classify each of these points, A, B, C, D, E, F, G, and H, as whether the function, let's say this is y equals f of x here, does f of x have a local min, max, or neither, or both at all of these different points? And we want to be very careful with the definition. Okay, so what about at x equals a? Does f have a local min? It clearly doesn't have a local max at x equals a. Does f have a local min at x equals a? And the answer is no. No min or max. So why not? Well, because x equals a is not in the domain of the function. F of a is undefined. Right? We've got that open circle there. So we cannot possibly satisfy this definition where f of c is less than or equal to f of x because f of x is undefined when f of c. The f of c part is undefined. So that inequality cannot possibly be true. Okay, cool. So yeah, a little weird, which means that you could have a function maybe that doesn't have any local mins or maxes, right? Even on like an open interval, doesn't have to happen. Okay, what about at b? So at x equals b, we might notice that the function gets, it's got a peak here, but the function gets bigger at other places, right? Like f of g, for example, is way bigger than f of b. But remember, we only care about local. So we only need to draw this little tiny interval around x equals b, which means we're only looking at the function values on this little bit of the function. And yeah, that's a local max. F of b is bigger than f of x for all the x's just in that little interval around b. So we would say f has a local max. Right? So we're saying f of b is greater than or equal to f of x for x near b. Okay, cool. That seems like kind of a good intuitive maximum. That's what a maximum should be, right? Not the global maximum. So b is not a point where f has a global maximum. The global maximum would be like on the entire interval from a to h, what's the biggest value that f takes? And that happens at g. But it is a local maximum nonetheless. Okay, and what about at c? Well, that's very similar, except it's a local minimum. So the function does get smaller at other points, like at h, for example, but nearby x equals c, we just draw a little tiny interval around x equals c. The function is smaller at c than it is anywhere else in that interval. So I would say at x equals c, f has a local min. Because f of c is less than or equal to f of x for x just in that interval for x near c. Okay, so those are kind of the simpler ones, I would say. Maybe g is also pretty simple, but d, e, and f are weird. So what happens at x equals d? So I'm looking at x equals d. I'm going to draw some little interval around it, which means I'm only considering function values here and here. Okay, so just that little piece. And turns out f has a local max. Yeah, it is a local max. Why isn't my eraser working? It has a local max. Why? Well, if we look at f of d, for the x's on the left of x equals d, f of d is greater than f of x, right? And if we look to the right of x equals d, f of d is equal to f of x for those x's. So it is greater than or equal to for the x near c, for the x near d. So that's a local max. Yes, it really is. It looks weird because of that stuff on the right, but that actually counts as a local max. What about x equals e? So maybe pause the video for a moment and try to figure out what is going on at x equals e. Does f have a local min or a local max there? Okay, so I'll wait. Go ahead. Okay, so I assume you paused the video and came back. And what's going on? Well, let's notice that f of e is equal to f of x for x near e, right? So in particular, f of e is less than or equal to, and f of e is greater than or equal to f of x. So both of those conditions are satisfied, which means f has a local max and a local min. At x equals e. So that may seem counterintuitive at first. A function shouldn't have a local min and max at the same time. But, I mean, that's part of the definition, is that we're including the equal sign. So you can have this sort of weird behavior. In fact, all the points between d and f have this property. So I would actually say that f has a local max and min at all x in the interval, the open interval, from d to f. It's true, not including d and f. At d and f, we don't have both max and min. But if we look at this, every point in this interval here has that property where the function's horizontal. So if the function's horizontal for some stretch of its interval, of its domain, then you're going to have a local max and min there. Okay, so let me come up, maybe up to this box on the upper right so I can keep the picture in view. What happens at x equals f? So at x equals f, what's going on with my function? Well, the function gets bigger to the right, so definitely not a local maximum. But I would say that f of x has a local min. So again, we look at a little interval around f, And on the left, the function is equal to f of f. And on the right, the function is greater than f of f. So yeah, I guess I shouldn't have used f for my input value, but you get the idea. So local min. How about g? Well, g is your favorite point. G is actually the global maximum and the local maximum. So we'll talk about global maxes a lot more later. But at x equals g, we just have a global max. Let me say that again. Local max. And what about x equals h? So remember, on the left side at x equals a, there was neither a max nor min because the function was undefined. But at x equals h, if I make an interval around h, oh wait, my interval, any open interval containing h has to stick out to the right a little bit, doesn't it? Yeah, because if it just stopped at h, that would be a closed interval with a little square bracket. But an open interval containing h has to stick out to the right. But what's going on with the function out to the right? Well, the function isn't defined. So that's why it's important that we only consider x's in the domain of f, right? So we only care about points in the domain, which means at an endpoint of the interval there, if that's the end of the domain of f, which it is in this case, right? I didn't draw the function anywhere else. Then we can still consider that to be a local minimum because we only have to be smaller than the f of x values for x in the domain of f. So I would still say that f has a local min here. Because f of h is less than or equal to all the f of x nearby that are actually in the domain. Okay, so yeah, some fine technical points here. Like I said, usually you don't need to be too careful with this. Most of the points look like what's happening at g, where you just have a hump or something. But, you know, it pays to see these things every once in a while. In math, we do like to be precise at times, so we know exactly what's going on in every situation. But yeah, so with that, I think we'll be done, and I'll see you next time.